The first order system, which I discussed just now, with the step input response. That is what I mentioned yesterday. For all the transient analysis, always the step input is considered for as input. So with the variation in k and the time constant tau, we get these two graphs. Now in continuation with this, for the steady state, you get these variables of simple first order system. So as I mentioned yesterday, simple first order system, you have along with R, one either a capacitor or an inductor. If you write KVL for this, what you get is, if step input, if I apply step input V of t, if I apply, the current flowing through this will be I of t. And you can write KVL as the voltage V of t, the supply voltage or the causal voltage or the input voltage or the driving force. All of them mean the same. Is equal to the drop across the resistance and the voltage developed across the capacitor. If you write it and simplify the equation, you get this V of t as RC into dVt by dt plus the state variable V of t. That is the variation in time as soon as you apply the voltage. So this is the step input response. With the help of the graph, we can analyze. This is what yesterday we discussed. Now we move on to, with this background, with the first order system, we'll move on to the second order system. Now in the second order system, as I mentioned yesterday, to get RC networks. Two RC networks. So compared to the first order system, a second order system is slightly complex because of the two poles which are present in this. And also the response is going to be different from yesterday. First thing here, the concept of time constant does not arise. If you have only one energy storing element, either L or C, you come across the concept of time constant. But when it comes to second order systems, where you come across two energy storing elements along with the resistor, the natural frequency of oscillation comes into picture, and also the damping factor or the damping coefficient. So you can see here the changes in the parameters. So a second order system can display characteristics much like a first order system depending upon the component values. Now component values are nothing but your RLC values along with damping and natural frequency of oscillation for its transient response. So the second order system, when you put it in the feedback loop, it looks somewhat like this. So where you come across the equation is like this, the transfer function or the equation where R of S is the input and C of S is the output. Usually in other books you might have found Y of S and X of S as output and input respectively. So basically the transfer function G of S can be represented as Y of S divided by X of S or C of S divided by R of S. And when you simplify, it gives you this equation. Omega n square divided by s square plus 2 zeta omega n s plus omega n square. That is in terms of the natural frequency omega n and damping ratio zeta. Before this, I will take up a step response of series RLC circuit, how we come to that transfer function. So before that, we'll see the transfer function for this first. So this is a simple RLC circuit with the step input applied here. Step input V of S applied. Now when I apply KVL to this equation, you get Ri plus L di by dt plus Vc is equal to the total input. So this Vc is nothing but, you can check here, Vc is the voltage developed across the capacitor or simply written as Vk. So that when I simplify, you get the equation something like this. I hope all of you know this equation. Here I can write simply this V. S of t is equal to, I can split this into two components, mainly the transient component and the steady state component. So when I write it like that, V of t is the total response, which is equal to summation or sum of the transient response and the steady state response. So here when we take up this equation, assuming that assuming that the initial conditions are zero, that is initial charges on the capacitor are equal to zero, and also initially the inductor is not carrying any current due to its earlier conditions. Assuming that it is a fresh start for these, that is the capacitance has zero initial charges and the current carried by the inductor initially is equal to zero. And as it is, we know R is a zero order component, so it doesn't have any initial conditions. Whenever we apply any voltage, the current is going to flow through R. If initial condition exists, then capacitor may have some charges on it. Due to this capacitor charges, this inductor may also carry some current through it. But when we assume that the initial conditions are zero, then the capacitor is zero charged and the inductor is also carrying zero current through it. Now come back to this equation where already we have written the equation. Then after simplification, after substitution for I, which is equal to C into dV by dt, substituting the values in equation 1, what we get is d square by dt into d square by dt of V plus R by L dV by dt plus V by L by C, where V is the voltage developed across the capacitor. Now here actually we come across different equations for each one of them. When we convert, this is actually in time domain. For simplifying the analysis, or it is easy for us to analyze in terms of few algebraic equations. So to make it simpler or to convert it in the form of algebraic equations, we prefer the transfer function analysis or S domain analysis. In time domain, what happens? We come across these differential equations. So when you come across differential equations, we can relate to time domain, but they no longer remain in terms of the linear or algebraic equations. So to simplify the mathematics, we prefer to convert them to algebraic form by applying Laplace transform. So after applying Laplace transform, what we get is different equations for the current through the circuit or the voltage across each element. It can be VR, the voltage across resistance, or it can be VL, the voltage in the inductor, or it can be VC, the voltage developed across the capacitor. So when you write the transfer functions for each one of them, you get the transfer functions like this. So I of S is equal to V of S divided by the total impedance. So it is simply the total voltage applied divided by the total impedance in the circuit. This total impedance in the circuit, when you in the Laplace, it becomes R plus Ls plus 1 by Cs. Further, you can simplify this actually. The further simplification gives you the next equation. I will share it. Here you can write. So simply remember that the current flowing through the series circuit, when it is converted to its Laplace, you get it as total voltage V of S again. And I hope you all know when we convert them to or when we apply Laplace, always we use the capital letters, and just to indicate that they are in Laplace, we write S in the bracket. So the current equation in Laplace is this. If you want the transfer function, it can be written as I of S by V of S or V of S by I of S. So that gives you the transfer function. So similarly, the voltage developed across the resistance R, that is VR of S, is equal to R into I of S. R into I of S, and I of S already we have written it as this. So simply it is I into I of S into R. Similarly, the voltage developed across the inductor, that is VL of S, is equal to SL into I of S. On the similar lines, the voltage developed across the capacitor is VC of S is equal to V, that is the applied voltage, divided by the factor 1 plus LC S square plus RC S, or simply it can be written as S square into LC plus RC into S plus 1. So this is the equation we consider for calculating the damping factor or damping coefficient. Now, whenever there is a RLC series circuit, or RLC parallel circuit with L and C in any combination, there is always a possibility of oscillations being developed. Now, when you have the oscillations being developed, the question comes, are they damped or undamped? Now, the undamped natural frequency of oscillation is given by something like this. Now, you can relate to this equation. This equation, omega n square divided by s square plus 2 zeta omega n s plus omega n square. Here, in the next slide, you have this equation. Yeah, omega n undamped natural frequency of the second order system, which is the frequency of oscillation of the system without damping. Now, what is this damping? Damping means basically whenever we have these RLC components, naturally, when these components are present in the system, whenever there is a R component present, the losses or the drop across that is bound to happen. Now, when there is a voltage drop, naturally in one form or the other, the heat is going to be dissipated there. So, the energy is going to be lost in the form of heat. So, this causes damping. Again, when there are L and C components, we for our analysis assume them to be ideal. But there is no ideal component as such. So, due to L and C components, the oscillations are being developed and energy transfer from capacitance to inductor or inductor to capacitance is continuously happening. This incurs losses. So these R, L and C components are responsible for damping of the system or power losses in the system. That's why your damping ratio is or zeta is defined in terms of RLC. And for a second order system, series RLC circuit, the damping ratio zeta is equal to R by 2 into the square root of L by C. Similarly, omega n, for this also, we have the equation which is equal to 1 by square root of LC. So the damping or the oscillations are going to be dependent on the value of L and C. And the level of overshoot or the damping which is going to be dependent on R, L and C. So remember these two. Omega n is nothing but the natural frequency of oscillations, which is equal to 1 by root L and C. 1 by square root of LC. And zeta is equal to the damping ratio, which is equal to R by 2 under the square root of L by C. Try to relate, whenever we are in S domain, try to relate these terms to RLC so that for you all it is easier to understand. Because when we start communicating in S domain, always we talk in terms of S roots of the equation, poles or zeros. But what are these poles and zeros? How they are related to our basic components R, L and C, try to always visualize them. I am giving here in the slides all those equations. So try always with RLC so that you know the impact of them in time domain. We can very easily relate to time domain because RLC are the components which we have used in our circuit and we know where exactly they are placed. But when we convert them to S domain, basically for all our mathematical modeling or mathematical simplifications, we want some algebraic equations which are easier to analyze. So we transfer to S domain. So try to relate the S domain and the time domain components so that you can relate any mechatronic system in time domain as well. So here omega n we know and zeta we know in RLC, as well as now we can relate here. So here actually I have given in terms of RLC only the equations, not in terms of only S, omega and zeta. So these are the Laplace transforms for current flowing through the circuit, the voltage developed across the resistor, the voltage developed in the inductor, and voltage developed across the capacitor. So this gives the transfer function of the response. H of S is the response. So now we'll go back to our S domain second order equation. So two poles of the system. As I mentioned, in your first order RC circuit, you have one pole. And in the second order system, you have two RC networks, which indicates that it has two poles. And the two poles of the system this equation, S1 and S2. These are the two poles. So here you can see one is with plus sign, the other one is with minus sign. Because they are R and C components which are equal in nature, so you have the values of these are going to be same, but only one is with a plus, one is minus. Okay. Now we'll try to place where exactly these poles can be placed on the S domain graph. See, this is the S axis and this is S is a, I guess all of you know what is this S domain graph, right? Where the y-axis is nothing but j omega axis and x-axis is nothing but your sigma axis. So S is equal to sigma plus j omega. Note this point. S is equal to sigma plus j omega, where sigma is your S x-axis and j omega is your y-axis. Now where exactly your poles are present? The one with the plus sign which is present here. The other one with the minus sign is present here. Now what exactly this damping, underdamping or undamping, where this zeta is equal to 0 represents the undamped state. Let me take you to second slide. So here you can check. So when we give step input, initially, that is the transient phase, you come across these parameters. So in the transient phase, your rise time, that is the TR, where It is the time taken to attain 63% of its final steady state value. And then you come across one more word, that is the maximum overshoot or the peak overshoot. So the time taken to attain this peak overshoot or the maximum overshoot is known as peak time, usually represented as TP, suffix P. So here you can see on the graph, MP is the maximum overshoot. The amplitude of the maximum overshoot is represented by MP. So yesterday we have discussed these rise time and settling time, also the fall time. So the same meanings hold good even for second order system as well. Now there is one more concept here, that is the delay time. So usually it is represented by TD. Suffix D indicates delay time. So the delay time is the time required for the response to reach half the final value. So you have the mark for half the final value, the 50% of the value, plus 63% of the value, plus the peak time and the final value or the steady state value. So these are the 4 time parameters you should remember. So here the different terminologies and 90%, 5% to 95% or 0 to 100% of its final value. So depending upon, you can see here the rise time is the time required for the response to rise from 10 to 90% or 5 to 95% or 0 to 100% of its final value. So here the definitions are changing. But whenever you are analyzing the equation, you see which type of the system you are analyzing, then stick on to these definitions. So here you can see individually what is the peak time. Peak time is the time taken for the first overshoot. So here the maximum overshoot is the maximum peak value. This is what we discussed. Now settling time is the one which is nothing but the time taken to attain the steady state value. So these equations, okay, you remember the equation which I discussed just now, how to arrive from the KVL to the transfer function. That is very, very important. These actually till second order system, all the analysis is done. As the complexity of the system goes on increasing with every system, for higher order systems, this analysis is not carried out. Here you can check, this is the MATLAB graph where with variation in the damping factor and the natural frequency of oscillation, how exactly the variation happens, this is what is shown. This is in the S domain. So don't go into the S domain. And whenever we have this, there is a difference in the input applied and the output coming. Immediately the output is not available. So it is taking some time. Then the question of this error comes into picture because it is not producing the exact response what we expected. So this leads to errors. And in the transient phase, this is called as dynamic error. And once the steady state is attained, this error is called as steady state error. So if the output of a control system or any mechatronic system at steady state does not exactly match with the input, there is some mismatch with the input given and the expected output, then the system is said to be having some steady state error. Now, how much error is tolerated? So this already the 12 parameters which we have discussed in the very first sessions, where the accuracy, the sensitivity, the error tolerance, and what type of error it is, whether it is human error or machine error or zero error. We have discussed all this, parallax error. So what type of error is this, and any correction can it be applied to get somewhere near expected results? All these things are actually considered when you consider the steady state error. In some systems, you may not have any steady state error at all. Exactly, there is a match between the input and the output. So whenever there is a exact matching between the input and the output, they there is one more word coming here, that is goodness of the system. So these errors indicate the goodness of the system. Now already we have discussed the control systems and the closed loop and open loop control systems in signal conditioning. Now when it comes to control systems, whenever you want highly accurate system, always there is a mechanism put in place how to control that to bring it to near zero error or highly accurate system or improved accurate system. So for that, you need to have your good control system in place. So when I say control system, we have feedback control systems, we have open loop control systems, or we have one step, two step, or three step control systems. So in one step, you can improve the accuracy or bring the solution near the expected one. Here basically the concentration is to design a system which gives you a system which is accurate enough to your application. For this often I have given example of a thermometer where the accuracy level of the thermometer, even 1 degree error causes lot of problems with the measurements. Whereas in case of say some water heater or something, 1 degree of accuracy may not cause so much of issues. So under such cases, your accuracy level, what accuracy you want a system to function at, or the desired accuracy level matters a lot here. So on the basis of that, you have different error analysis, and for these errors, the compensation network design or the compensation circuitry is designed to bring the error under control and give you the output as per your requirement. So here this is all your error analysis. Already we have done it. So don't want to go into the details of this error analysis. Steady state and first order, second order. So what I will do is take you to directly this summary where for a type 0 system for step input, so these are the different constants in terms of this K. K or A, this is nothing but the output by input ratio. This K is nothing but output by input. We have checked for an amplifier if output by input ratio is equal to 10. Say the DC gain it is usually called as. So this is the ratio. So if this DC gain, it is always expressed here in terms of the DC gain or the K ratio, or even it's also called as A. So for a type 0 system, for step input, it is 1 divided by 1 plus K, and for the ramp input, it is 1 by K. Here, this infinity or 0, they indicate that this is a condition where it cannot be used at all. Also, this is the condition where this cannot be, the system cannot be designed around this. So these are the values where for type 0, type 1 and type 2 systems, you have the errors, steady state errors. So with this understanding, we'll see how a DC motor which is having multiple series systems can be designed, or you can form the transfer function of this. I guess you have class now. Sir or madam is taking. Do you have a class now?
Not sure, ma'am.
Yesterday, what happened? You had maths class.
No, we didn't had.
Then who is taking that?
Like I checked with Shailesh sir also. He said that he will inform soon, but
Okay.
it is not yet informed.
Okay, fine. So in that case, okay, just check with him. If anybody is taking, go ahead with that. If you don't have tomorrow,
Okay.
if I can extend that class, I will plan for that. By
Uh,
evening, if you can inform me, I will be able to engage that class as well.
okay, ma'am. We'll check
Huh?
and inform you.
Yeah, please. By today evening, you please inform me so that I can engage tomorrow and even day after also, continuously 2 hours if I can engage, that would be good.
Okay, ma'am.
Okay, yeah.